Hello students, welcome back to the science class. In this class, we will continue with the same chapter gravitation and discuss some more concepts about this. Okay? Students, let us now discuss the two questions those are given in your book. Two in-text questions. Question number 1 says, state the universal law of gravitation. So, the answer for that is, the universal law of gravitation states that every object in the universe attracts every other object with a force called the gravitational force. The force acting between two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So, for two objects of masses m1 and m2 and the distance between them r, the force F of attraction acting between them is given by the universal law of gravitation as F is equal to g m1 m2 divided by r square, where m1 and m2 are the masses of two objects and r is the distance between two objects. And in this case, as we have already discussed, g is the universal gravitational constant and its value is 6.67 into 10 to the power minus 11 Newton meter square kg to the power minus 2. In some cases, while calculation, we take 6.67 as 6.7. We just round it off because of easy calculation purpose. Okay. So, students, let us now discuss question number 2. It says, write the formula to find the magnitude of the gravitational force between the earth and an object on the surface of the earth. Okay. Now, let us go for the solution of question number 2. So, for the solution, let ME be the mass of earth and M be the mass of object on the surface of earth. Fine. And let R be the radius of the earth. Fine. Then, according to the universal law of gravitation, the gravitational force F acting between the earth and the object is given by the relation F is equal to G m E m by r square. Okay. So, this is the force which is acting between the earth and the object that is lying on the surface of the earth. Okay. Students, let us now discuss another concept of gravitation, that is importance of the universal law of gravitation. The universal law of gravitation successfully explained several phenomena which were believed to be unconnected. Those are the force that binds us to the earth, the motion of the moon around the earth, the motion of planets around the sun and the tides due to the moon and the sun. Now, let us discuss about free fall. Okay. Students, you can understand the meaning of free fall by performing the activity that is given in your book. What you can do? You can take a stone, throw it upwards, it reaches a certain height and then it starts falling down. That means it falls freely. Okay, it reaches up to a certain height. After that, without any delay, it tries to come down to the earth's surface freely. So, this is called a free fall. We have learned that the earth attracts objects towards it. This is due to the gravitational force. Whenever objects fall towards the earth under this force alone, we say that the objects are in free fall. So students, as we have understood that the object falls freely because of gravitational force. So is there any change in the velocity of falling objects? While falling, there is no change in the direction of motion of the objects. See, if a stone falls from upper direction, it does not change its direction in between. It falls in a particular direction. But due to the Earth's attraction, there will be a change in the magnitude of the velocity. Any change in velocity involves acceleration. Whenever an object falls towards the earth, an acceleration is involved. This acceleration is due to the earth's gravitational force. Therefore, this acceleration is called the acceleration due to the gravitational force of the earth or acceleration due to gravity. It is denoted by g. So, g is nothing but the acceleration due to gravity, and the unit of g is the same as that of acceleration, that is ms to the power minus 2. This is the unit for acceleration due to gravity. It is same as the unit of acceleration. We know from the second law of motion that force is the product of mass and acceleration, that is F is equal to ma. This is according to Newton's second law of motion. Let the mass of the stone in the activity which I have already told you to do by yourself, let that mass is equal to m. Let us find out something. Okay. We know from the second law of motion that force is the product of mass and acceleration. So, let the mass of the stone in the activity be m. So, mass of stone, that is taken as m. Fine. We already know that there is acceleration involved in falling objects due to the gravitational force and is denoted by g, that is g, acceleration due to gravity. Okay. So, if F will be the magnitude of the gravitational force, then it will be equal to F will be equal to m into g. As we know, force is the product of mass and acceleration as per the second law of motion. Here acceleration is substituted by acceleration due to gravity, because as we have already discussed, the stone is free falling, and because it is a free falling object, gravitational force is acting upon it, and that is why the acceleration is substituted by the acceleration due to gravity. Fine. Now students, we have already found out that F is equal to g m by d square. Okay. So, if I substitute the value of F which I have got from this equation over here, we will get mg is equal to g m by d square, isn't it? So, I can now cancel out both the m. That means acceleration due to gravity is equal to product of gravitational constant and mass divided by d square. Okay. So, acceleration due to gravity is equal to product of gravitational constant, mass divided by d square, where mass m is the mass of the earth and d is the distance between the object and the earth. Okay. Let an object be on or near the surface of the earth. The distance d is equal to r in this case, because we know that while an object is on the surface of earth, so distance is nothing but the radius of the earth. So now let us put that r in this formula. So in such case, when a surface is lying on the earth, okay, so for objects on or near the surface of the earth, force, that is mass into acceleration due to gravity, will be equal to g m by r square, where r is nothing but the radius of the earth. When I cancel out both the m's, acceleration due to gravity will be g m by r square. Fine. So acceleration due to gravity, that is g, is equal to product of gravitational constant and mass of the earth divided by square of the radius of the earth. Hope you have understood this. Students, the earth is not a perfect sphere. As the radius of the earth increases from the poles to the equator, the value of g becomes greater at the poles than at the equator. For most calculations, we can take g to be more or less constant on or near the earth. For the objects far from the earth, the acceleration due to gravitational force of earth is given by g is equal to gm by d square. Okay. So we always use this formula whenever we do some calculation. Okay. Hope you have understood this concept. So students, let me tell you something about Sir Isaac Newton. He was born in Woolsthorpe near Grantham, England. He is generally regarded as the most original and influential theorist in the history of science. He was born in poor farming family, but he was not good at farming. He was sent to study at Cambridge University in 1661. In 1665, a plague broke out in Cambridge, and so Newton took a year off. It was during this year that the incident of the apple falling on him is said to have occurred. This incident prompted Newton to explore the possibility of connecting gravity with the force that kept the moon in its orbit. This led him to the universal law of gravitation. It is remarkable that many great scientists before him knew of gravity but failed to realize it. Newton formulated the well-known laws of motion. He worked on theories of light and color. He designed an astronomical telescope to carry out astronomical observations. Newton was also a great mathematician. He invented a new branch of mathematics called calculus. He used it to prove that for objects outside a sphere of uniform density, the sphere behaves as if the whole of its mass is concentrated at its center. Newton transformed the structure of physical science with his three laws of motion and the universal law of gravitation. As the keystone of the scientific revolution of the 17th century, Newton's work combined the contributions of Copernicus, Kepler, Galileo and others into a new powerful synthesis. It is remarkable that though the gravitational theory could not be verified at that time, there was hardly any doubt about its correctness. This is because Newton based his theory on sound scientific reasoning and backed it with mathematics. This made the theory simple and elegant. These qualities are now recognized as essential requirements of a good scientific theory. Now let us discuss how did Newton guess the inverse square rule. There has always been a great interest in the motion of planets. By the 16th century, a lot of data on the motion of planets had been collected by many astronomers. Based on this data, Johannes Kepler derived three laws which govern the motion of planets. These are called Kepler's laws. These are: the orbit of a planet is an ellipse with the sun at one of the foci, as shown in the figure given in your book. In this figure, O is the position of the sun. The line joining the planet and the sun sweep equal areas in equal intervals of time. Thus, if the time of interval from A to B is the same as that from C to D, then the areas OAB and OCD are equal. The cube of the mean distance of a planet from the sun is proportional to the square of its orbital period t, or r cube divided by t square is equal to constant. It is important to note that Kepler could not give a theory to explain the motion of planets. It was Newton who showed that the cause of the planetary motion is the gravitational force that the sun exerts on them. Newton used the third law of Kepler to calculate the gravitational force of attraction. The gravitational force of the earth is weakened by distance. A simple argument goes like this. We can assume that the planetary orbits are circular. Suppose the orbital velocity is v and the radius of the orbit is r, then the force acting on an orbiting planet is given by F is directly proportional to v square by r. If t denotes the period, then v is equal to 2 pi r divided by t, so that v square is directly proportional to r square by t square. We can rewrite this as v square is directly proportional to 1 by r into r cube by t square. Since r cube by t square is constant by Kepler's third law, we have v square proportional to 1 by r. Combining this with f is proportional to v square by r, we get f is proportional to 1 by r square. Okay? Let us discuss some questions. Those are given in your book. What are the differences between the mass of an object and its weight? Okay? So, let us discuss this question. Student, we can differentiate between mass and weight in the following way. We should use four properties to differentiate between mass and weight. Okay? So, what is mass? Mass of a body is the measure of its inertia. But what is weight? Weight of the body is the force with which it is attracted towards the earth. That is why W is equal to mass into acceleration due to gravity. Second point, SI unit of mass is kilogram and that of weight is Newton. Third point, mass remains constant everywhere as we have already discussed, but in case of weight, its value changes from place to place because everywhere the force of gravity or the gravitational force is not constant. The more we go away from the earth's surface, the gravitational force keeps on decreasing. That is why value changes from place to place. Fourth point, mass is measured by common balance, okay, but weight is measured by spring balance. Students, what do you mean by common balance? See, you might have seen this common balance in vegetable markets, okay. In the market, vegetables are weighed using common balance, but spring balance, have you ever seen it? I hope so. Spring balance is used to find out the weight of the object. Okay? So, in this way, we differentiate between mass and weight. Students, let us now discuss the next question. The next question says, why is the weight of an object on the moon 1/6 its weight on the earth? Let us now discuss its solution. Okay? The weight of an object depends on the value of acceleration due to gravity g. The value of g on earth is 6 times more than that of moon, because the mass and radius of the earth is more than the mass and radius of the moon. So, let us understand this in a better way. Okay? Students, we have acceleration due to gravity g is equal to gm by r square. So, we have already discussed that g is equal to gm by r square, and we have weight as mass into acceleration due to gravity. So, weight of a body of mass m on earth is WE, that is weight on earth. Okay. So, mass to acceleration due to gravity at earth, that is equal to, just concentrate, this is weight of the body on earth. Okay. So, when I replace or substitute the value of g over here, I get mass, and what is acceleration due to gravity? That is gm by r square, and in case of earth it should be me by r square. Fine. So, weight of a body of mass m on moon is Wm, that is mass into acceleration due to gravity at moon, mass moon by r square. This is square of radius of earth and this is square of radius of moon. Okay? We have already discussed these things. Now, if we find the ratio, what we get? Ratio of weight of the object on moon to that of the weight on earth is equal to, what should it be? See, this divided by this, m g m m by r square, okay, divided by m g m e by r square. For differentiation in radius, we can also write, that is r m and r e, that means radius of moon and radius of earth. Fine. So, we can clearly distinguish between them. So, this will give us m g m m by r m square into r e square divided by m g m e. Okay. So, we can cancel out both this. So, what is remained? That is mass of moon into radius of earth square divided by mass of earth into radius of moon square. Okay? So, as mass of moon is 1 by 100 times the mass of earth and radius of moon is 1 by 4 times the radius of earth. So, we can write Wm by We is equal to into square, okay, and that is equal to 1 by 100 into 4 square. So, that is about 1 by 6. Fine. So, students, here is the solution for the question. As the question says, weight of an object on moon is 1/6 its weight on the earth. We have found out that weight of the object on the moon is 1/6 that of the earth. Okay. Hope you have understood this. Students, with this we have come to the end of this session. In this session, we have discussed some of the concepts of gravitation. In our next class, we will discuss some more concepts about gravitation. Till then, go through your book, revise the concepts which we have studied today, and we will meet soon again. Okay? Keep smiling, keep practicing. Thank you.